Okay, first of all, we had a temporary transfer of the spoon. Bert found a bug. Do we have our intelligent computer? Is it working? So he wants to go back to swap. He says that if we look at our, where is our third swap, this swap, it sometimes will not work. And this is an amazing thing because we actually have a proof that it does. So you see we have a correctness proof, but then it doesn't work. What is the assumption in the proof? No. That A, B are different objects, because if they happen to be the same object, sad things will happen. All right? So
object could still be different, but they could be equal in value, right?
That is perfectly fine. If the objects are different, our proof works. And if it's the same object, whatever the value it contains, at the end of this function, it will be always contain 0. Because it will just, every bit will be zapped completely, totally, and absolutely. So, did I say absolutely? Yes. So, that's actually a quote from a famous book, Maltese Falcon. Now, how do we fix it? And that is a relatively common situation, because often you write a code, for example, you want to implement something like assignment, and you go say, well, first I'm going to clean up this, and then I'm going to construct it. And it works like a charm, except till the moment somebody writes assignment from A to A. Because you scrape A on the left-hand side, and then you attempt to copy from the right-hand side, which happens to be the same value. So there is a standard solution, Bert.
If you could just say if ampersand A doesn't equal ampersand B, put the rest of it in side braces.
Yeah, that's pretty clean, I think. It's basically don't attempt. Basically, what you are saying is what? What you are saying in English?
If it's the same object, don't do anything.
Don't swap guy with himself. No need to do any work, which happens to be true. Right? In some sense, one could even argue, let me try to argue, say, maybe it's always good to do that. Maybe we always should check for that. Is it a good idea or not? What do you think? Why not? Will it be faster?
Depends on how you use it.
But what is, let us write the code. Did we write the code? No, and then we just left? Oh. No, let's keep looking in that code. So what is the general rule?
General rule, don't do anything you don't have to, I guess.
But it's a different general rule I'm looking for here. So this is true. This is what it says. You don't have to, don't do it. But there is additional rule which says that actually we could write this code up there, couldn't we? In the first code. Should we? Should we or not?
No.
Why not?
It's just more work than common.
That's the rule. Did you hear what you said?
It's more work in the common case.
That is, sometimes we're very tempted to say, well, but if it's 5, I have a fast path. So we put in all of our code, if 5 fast path, whatever, I mean, relevance code, any code. what you do not understand could be in relevance code. So probably is in relevance. Anything there is in relevance code. That's my experience there. For nothing personal, because there's just layers and layers of different styles. So there is a grave temptation always to say we will optimize for 5. But Nick is right, because what we do, we're going to do the check every time. And assuming that we have many integers, more than 3, then we're going to only seldom hit 5. And we're going to be doing the check all the time. So we sort of need another rule, which is don't do things unless necessary. But the other rule is do not optimize uncommon cases, right? Because you will have to check every time for 7, 6, 11, other cases, right? So this is, spoon goes back. 6 is not prime. We never swap non-primes. That's true. But, okay. We go back to min. Because we're not done with min. Not even close. Okay. There are 2 things. There is one thing which, since we talk about this reference, there is one problem. This actually, except for the body, which has major problems, the code, the interface is the same, is in the standard. So reference, reference, return a reference. The idea indeed that you could compare 2 things, say where is less water here, and you don't need to copy, you just, it's always better solution. Sadly enough, your first intuition was actually correct. What you wanted to say is TREF. You might not have thought it through, but it's actually a great idea, because if these things are mutable, you really want to be able to say, I want to fire or do something bad to the minimum guy. And now you cannot do that, because if I give it non-constant references, the silly thing will return a constant reference, and if I attempt to mutate, it will not work. So there is a problem there, again, which is still not solved in the present C++, which is basically what I want. I want to have a function which, if they're non-constant reference, will return non-constant reference. If there are constant, or at least if only one of them is a constant reference, then it will return if you know what I mean? If one of them is a constant reference, it will return a constant reference, right? Because it has to. But just, it cannot be done cleanly, so we're stuck with this, right? But it's a limitation, because in those cases, which are practical cases where you want to find smaller, and let's not fire him, let's give him a raise. Like Vinay is a manager here, he looks at his employees and this guy makes too little. I guess realistic situation, right? So he wants to give him a raise. He cannot, because he gets back constant. Do not ever complain about your pay to him. He cannot. It's all C++ fault. So, so what we now need, I also told you, there's also the problem with the implementation. And it seems to be correct in a sense, it does seemingly the right thing, but that's the problem, guys, in every way in programming. You do something and it seems to be correct, but you have to think deeply, and then you discover a problem. And somebody mentioned it. Do you remember what he mentioned?
If they are equal.
Which one do you return? it seems that it doesn't matter. Now, as a matter of fact, it will take me quite a long path to show you why it does matter. Okay, let me explain to you in English, but then we will do a computer science path. You see, functions, when you design, this is another sort of thing. When you design a function, we often think about, I'll just design this function, and we ignore how it interacts with other parts of your API. And then you discover inconsistencies. And inconsistencies could be very, very subtle, but very painful. And what we shall see, by the way, if I ever finish this story, that I make these mistakes. There are several profound mistakes in STL where they're still in the standard. All of my attempts to change them, it's very easy to make a mistake. It's very hard to fix it. But we shall see that things like that actually matter. Let me explain why. Simply speaking, what we want to have is let me just construct a proof. We want to have the following thing. We want a sort to do no operations when things are sorted. Do you agree? It's sort of a good requirement. If we have things which are already sorted, we don't want them swapped. That's a good requirement. The second requirement is that if I sort two things, the first guy should be min after they're sorted. And the second guy should be max. Does it sound plausible? Well, remember we agreed that default ordering for sorting should be ascending. Do you remember why? Natural ordering of natural numbers, ascending. We don't go down from 0 to something, we go up. That's the natural. So 0, 1, 2, 3 is natural. 3, 2, 1, 0, it's when you launch missiles, whatever. But, so therefore we want, when we sort two guys, we will talk about eventually to n, we'll get to n, induction will work. But first we need to figure for two. We need the following thing. If they're equal, we don't want to move them, and after we sort them, first should be min, second should be max. Now, you see, what are you going to do? You are going to return b for min even when they're equal. You say, but they're not distinguishable. They're not distinguishable now, but they might be distinguishable. We'll get to that in a second, right? So I actually claim it's a good rule for min, but we'll have to prove it. It will take me a path to prove it, that min for equal arguments should return the first guy. Does it make sense? Right. But I know that we have to discover it fully. Now, so we need to change the code a little bit. So only B wins only if it's less. Right? On equal, A, we're not going, basically, when we sort, when we'll get to sort, we're not going to swap unless necessary. All right? Now, there's one line missing.
Requires the comment required.
Requires, yes. We need to figure out when will it work. Anybody has an idea? Actually, you.
T is regular.
T is regular, which is true. But it's not quite what we need. Remember I told you that sort of, for Paul and me, that would include that. For the official people in C++ standard, they're thinking semi-regular, regular, totally ordered. Right? So we know what to say. Yes? What do we say? Oh, it's already there. He reads our minds. What does it mean, by the way?
That means the less than operator is defined, the comparison is defined.
Anything? What if it just returns random true false? Is it a good total ordering?
Anti-symmetric. Transitive.
As long as it's consistent.
Very good, very good. There's the third one, yes. So what, okay, let us think, we will, well, it's more complicated than that. There should be some connection between less and some other fundamental relation. What is the other fundamental relation? You should have said that. Equal. That is, there should be a connection between less than and equality. Right? And again, here we encounter what is, programmers do need to know mathematics. They have to know certain fundamental things. First of all, less we assume that it is anti-reflexive. That is, it's an other term which we will encounter, that it's strict. A is not less than A. It's strict. And this was a choice I had to make. This is a less self-evident choice. What to pick up as a fundamental relation? Do you pick less or equal? Both of them would give you roughly the same universe of things. Okay? But somehow I thought that this requires a little less typing. There are other reasons. But for things like that, you need strictness. You need to have that A is less than A. You need a very important relation for any ordering. Any ordering, whether it's total ordering or any ordering, has to be, you said that? Never mind now what you said. Transitive. Transitivity is the main proper term. Do you remember what transitivity is?
Yes. If A less than B and B less than C, then A is less than C.
Very good. So transitivity is important. Why is it important? Think about sorting. If I checked that B wins over A, then I check that C wins over B, I don't have to do the third check. It's guaranteed. I could derive, I could assume that. Otherwise, sorting on many other things collapse. I mean, it's useless. Right? So transitivity is important. But then for total ordering, there is third very important thing called trichotomy law. From the name, what do you think trichotomy means? That one of three things is true. That's not trichotomy. One of the three, yes?
Less than, greater than, or equal.
Yes. That when you look at two things, they have to be either this is greater or this is greater, or they're equal. Nothing else. One of the three will be true. This is fundamental relation. It would be nice if somebody even marked it totally ordered means this, this, and this. But that's all right. They could. It's all in Wikipedia, or for those of you who so desire, there's this wonderful book written by two great computer scientists, Paul McJones and Alex Stepnev. If you ask, you could get for free. And there's a whole chapter dealing with just that. So, I always peddle my book, but the price is right. So, it is in my office, so you have to stop by. I'll peddle it only every third lecture, so I promise not to overdo it. It's very embarrassing, when you get to the point where you say, "Oh, please take it; it's free," and nobody is taking it. Okay, but it's very difficult book, of course. So we rewrote that. We know what it's true. Now, however, what we realize, this is a little bit too restrictive. It's a good general case, sort of that it's totally ordered. But is it the only thing you think you want to do min on? Partially ordered is really tough. This is what people think. If it's not totally ordered, it probably means it's partially ordered. Problem with partial ordering, if you check, is not every two elements are comparable. So nothing like that could possibly work. You could get into lattice theory, but there it's different. It's not max and mean, but infants, soup, this soup and infant. So they're different. So it's not called partial ordering. It's the right idea, the wrong name. Try to come up with an example. Come on, guys. That should be easy. You're not mathematicians. Unlike mathematicians, you actually deal with things called structs. Do you know what structs are? Things which have multiple fields. And you could have ordering on one. It's not going to be a total ordering. For example, you have employee record. And you order them by last name. Especially if you're in China, there will be very many people in the same buckets. Because, the set of last names is small, the number of people is very large. Right? So there will be people which are not less nor equal, nor greater, but they're not equal. Right? For example, there are two Stepanovs in this building, you might know, right? So when we look and compare only by the last name, one Stepanov is not greater than the other Stepanov. Do you agree with that? It's exactly the same string. Of course, I know who is superior, but do not repeat what I said. But, we are equivalent, but not equal. Right? So what you want is, could you?
Partial total order.
Well, the term which you're looking for is weak. It's not partial. Partial means you couldn't compare always. Weak means you can compare. It's exactly the same as total ordering. But in total ordering, trichotomy says it's greater or less or equal. And in case of weak ordering, it says it's greater or less or equivalent. There's some equivalent relation. Same last name. It's an equivalence relation. Right? Of course, you need to know what equivalence relation is, but I'm not going there. You have to figure out on your own. So how could we do that? You see, I actually claim that there are some people who say, oh, very simple, we'll define less than to be weak order. That's evil. Why is it evil? Why is it evil?
Going against 1,000 years of
Different
tradition.
cases.
What? Going against 1,000 years of tradition,
Speak.
of mathematical tradition.
Which one?
Which mathematical tradition?
Yes?
I don't know. Western mathematics?
No, I mean specifically. You see, specifically, all of you know the following thing, that if this is not true, what is true? Greater or equal is true. Right? Not greater and equivalent, greater and equal. You know that. So as a programmer, when you assume that these are not equal, A is greater than B is not true. You assume that B is greater or equal, whichever way, right? So, and that you cannot for weak ordering, right? So there is a firm rule in general: use overloaded symbols for what they commonly mean, which is what they. And if you say, I don't know any mathematics, fine. Just look at C. In every C data type where this thing is defined, its negation is this. This goes with, so when you extend it to other types, almost, yes, we will get to that, I promised long time ago. Well, it's true whenever we don't break all the laws of logic. So we will get to it in a few seconds. All right, so how would we do that? Anybody can propose solution?
Change the API, provide the method compare.
Yes. I'll pass this one, why not? Since he wants to be tortured, let him be tortured. So how would you do it?
Add another parameter. Oh,
Add another parameter. It's a great idea. I mean, where you don't know how to add another parameter. Okay, what would you call it? Let's start. He's going to tell us. Compare, yeah. There's a good name for it. Yeah? Compare. Yeah? No, I'll just compare.
Just that compare.
And what you would call the actual thing?
it should accept.
Never mind what it should. I mean, what would you call? That's all simple problems.
CMP.
CMP is a good choice. Yes. CMP. And could we change the body? Do we need to change the body?
Yes, we need, instead of B less than A, we should pass a call to compare with A and B.
No, I don't think so.
Or depends on how compare.
No. Just think. Everything you say is correct up to a point. So write what he wants, and then we'll see why. That's what he wants, I know. I think it sucks. Because we just went through a long discussion why we don't.
It should return something like less than 0.
Yeah, it should return something, but it's still wrong, whatever it returns. You see, it should behave. Ryan, could you, on the side, write what we used to have?
Oh, B and A?
And it makes a difference, you know. Basically, if you plug less than back into your code, it still should work. Do you agree with that? Right. So, and to say, oh, this is a little thing. Well, nothing is little. This is, in some sense, this is the whole point of my class. There is nothing little in programming. You know, it's all about, I mean, we are little people doing little things, but they're awfully important and wonderful. So, okay, now what do we need to do?
Implement compare.
No, we don't need to do that. That's the client needs to do that. But what do we need to do right here? Something is awfully wrong now.
Compare B and A will.
Now, this is what let me tell you, the code is just fine. But something is awfully wrong there. What's awfully wrong? Required. C doesn't have to be totally ordered. First. But what do we need to know? We need to have a requirement which connects what? First of all, I mean, this would not even work for, before we get, just let's leave it like that, this wouldn't work. Why wouldn't it work? It wouldn't compile. Why wouldn't it compile? Why wouldn't it compile? Where would you define it?
You need to define it.
So tell him.
Yes. So it should be, say, Boolean.
No, no, no. It's all very simple, guys. First of all, put a comma there. It's always a good start. Comma. You need one more type. This is a type. Where do you get this type from? Do you need, I mean, otherwise it wouldn't compile. It would say, compare is not defined. And guess what? It is not defined. He never said that. So, oh no, I didn't mean it, but you have to wait. Because you have to define every type. It has to be, I mean, guys, sorry that I do that, but I think it's important. And, yes, and all of you will eventually get the spoon and be tortured, yes. So maybe the next class nobody comes. So, I mean, some people, clever people like Sunil, see, he's not here, he knew. So, okay, now, what do we know about compare in C?
So the compare should work on the type key, right?
Compare is what on type T?
Is a operation, probably.
It's a particular kind of operation. We just called it. What is it called? Anybody remember? Now, of course, it's a functor, but it's mathematically, what kind of thing is it? No, it's not equivalence.
Binary operation.
It is a binary, but there are many binary operations. A plus is a binary operation. It wouldn't work with plus, would it? No, it wouldn't. Makes no sense either, even if it did work. For sometimes it will, because it will convert to bool and do some crazy stuff, but it's not what we intend. So what do we intend? We just spend time. It has to be less than what was less. What was less than? Do you remember what it was called? Total ordering. Yes, and this is what? Weak ordering, strict weak ordering on. Why don't we say that?
Okay. Strict weak ordering on T.
Strict weak ordering on T. Right? And you say that, well, it will compile without it. Yes, but what will it do? And here of course, I covered roughly 5% of what I planned to cover in this class, but I think do we make progress? I think we're making progress. So I'm not particularly concerned with what I covered. I have to go back and finally address the issue which sort of will cause us lots of trouble in practice. For example, people at Google encountered it and they couldn't figure out what's going on. You see, we assume that certain things, I mentioned that certain things work. For example, we assume that A is always equal to A. It seems to be natural. And then we assume that either A is less than B or B is greater or equal than A. Yes, we sort of assume that. This is not true, guys. There is said exception which causes enormous amount of harm, which sort of breaks all the laws of equality or ordering. And we will have to sort of eventually figure out what to do. It's a complicated problem. But let me tell you, let's write a little program. Could we write a little program? let's have a file called example.cpp. And in it, we will write, let's quickly write a function, which will, it will have function check equality. It will take, it will be returning void. It will be template taking type T, template of type T. And T will be, say, regular, because we will need equality. And we will take A by reference, Tref, A, and then we will print something. So we say stdc out, put out. That's apparently how you're supposed to say it. Bjarne taught me something last Friday. You're supposed to say put to. This is pronounced put to. Cout, put to. No. This thing is called put to. I didn't know it till 5 days ago. But now it's also, some other people call it insert. Some people call it input. But Bjarne calls it put to. So cout put to conditional expression, which will take A equal A. Well, what could we do? We could do, yeah, equal A. We'll say yes, and otherwise we'll say no. Do you agree that this thing should always print yes? You do not agree? One shouldn't it? No, I'm not asking what it.
If someone has overloaded equality to do something.
He needs to be, some operation should be done on his private members. That's for sure. I mean, because it's not equality. What he defined is not equality. No. This is what we're talking about, what must be. Right? Now, no programmer could live in the world if equality does not mean equality. Right? So, yes, you could do all kinds of things. But more important thing is that this will not print yes, at least in one case. Let's write a main. So we will take a main, and we will declare a variable of type double initialized to 0 divided by 0. Could we do that? Could we then apply a wonderful function to x? It's not a, it's called I. Is it called IOStream? Yes, it's called IOStream. Do it. F in octal constant. No. 0.0, it's double. 0.0. 0.0. This, it's a bad number, but nevertheless. Right? We'll talk about it. Yes, you do need parens around. Yeah, that. It says no. Right? And you could say, well, but only total idiots will write code like that. Problem is much harsher. Problem is that you could have a floating point computation which leads to this result in utterly invisible to you. Sort of the problem actually appears when people do some complicated things and occasionally get this, something like that. And they run millions of them. And then they merely say, let us sort them. And sort assumes that equality and inequality work like equality and inequality, and things happen. We will see how, right? So this is one, IEEE floating point standard is one of the great accomplishments of sort of computer science. In some sense, one of the top 5 from my point of view. We haven't got that many accomplishments, guys. But so, we might have 6 altogether. So, and some people like Paul and I, we remember how terrible it was before they did what they did. But they somehow decided to indicate undetermined floating point value by breaking fundamental logical axioms. And that causes this problem, and then it causes another problem. Let's try it.
So two undetermined are not equal.
They are not equal, and they are not equal. Let's go and replace equal with not equal and rerun it. This is, what did you do? Let me show. Well, okay, let me tell you what doesn't work, since I have it written in front of me on a piece of paper. So if you write the following thing, what do I have written in front of my piece of paper? If you say that A is less than A, or A is greater equal than A. Let's see what happens. One would assume that should be true, right? No, it's not true. So the problem is that for both equality and less than, you have a surprising relation. And in case of inequality, you have, at least in case of equality, the not equal sort of works. But in case of ordering, neither less than nor its negation hold. So the excluded middle doesn't work anymore, which is sad. And you could say code doesn't depend on it. Yes, it does. We shall see. You make reasonable assumptions, and then you get into that. So this is something which you need to consider. What's the solution? You basically, what I claim, the theory holds, which is you still have to maintain that equality means equality, less that means less that. And then you define singularities. You say there are singular values. And the universe collapses, nothing applies. So you have to assure that singular values do not appear in your computation. So we shouldn't there are two solutions: abandoning the laws or putting a wall around bad values. And I'm advocating the second one. We keep the laws, because otherwise things are, all right? So let's go and look. We have about 2 minutes. Let's go. Min. Okay, so for those of you, let me outline what we're going to do in the next. So for those of you who want to at least think about it, we obviously need to think about how min relates to max, right? And you say, oh, this is trivial. Guys, nothing in the world is trivial. Then we have to again think about sort 2, how to sort 2 guys. We have the technology for sorting. We know how to compare now, and we know how to swap. I claim that that's pretty much all the technology we need to sort 2 elements. But and then we need to find out how it relates to min max. Then I'm telling you the plan so that you know where we're going before we go there. Then we will have to look at the following more interesting algorithms. Remember I said that the third thing is linear search. But instead of doing linear search, we're going to look at generalization of min and max to a range. Now, we figured out if you have 2 elements, how to find min. we'll have to write an algorithm for finding min if you have a bunch, a range of elements. And then max. And then min and max together. Could we do it better? And then we're going to look at a wonderful problem of selection of two elements. Those of you who have plenty of time and nothing to do, there's a wonderful section in Knuth on called order selection in volume 3, where the problem is finding largest and second largest element. Try to think about how to find largest and second largest doing the minimal number of comparisons. That's the tricky thing. So you could read it in Knuth or you could think about it. In any case, you don't have to do anything because we will do it in the class. All right? See you next week if you survive. The spoon.